Imagine taking a bite out of your sandwich, and instantly, a bite disappears from the exact same spot on your friend's sandwich across the room. In programming, this kind of accidental sharing happens all the time when we work with containers inside of other containers. Picture a large backpack that holds two smaller lunchboxes, and inside those lunchboxes are your numbered snacks. In Python, we call this a nested list. We build it using these square brackets. The outer pair represents our main backpack, and the inner pairs represent the separate lunchboxes holding the actual data. Eventually, you will need to duplicate this entire setup. You want a second backpack to experiment with, without accidentally messing up the snacks inside your first one. Python gives us two different commands to copy data. Depending on which one you choose, the results are completely different. If you tell the computer to simply copy a nested list, it does exactly what you ask, but not as thoroughly as you assume. You have to be specific. Otherwise, you risk accidentally destroying your original data. Let's look at the first method, known as a shallow copy. It sounds like it should give us a brand new, fully stocked version of our data to play with. When we write b equals copy.copy a, we do get a new outer container. Here, we have a new green backpack sitting right next to our original blue one. But look inside that new green backpack. There aren't any new lunchboxes in here. Instead, it's empty except for these glowing, magical strings. A shallow copy doesn't duplicate the items stored inside the container. It only creates connections. Think of them as invisible portals that point directly back to the lunchboxes inside the original blue backpack. Watch what happens if we try to change a snack in our new copy. We type B00 equals 99. We follow the string into the first lunchbox and replace snack number 1 with 99. Because both backpacks are pointing to the exact same lunchbox, replacing the snack for the copy also replaces the snack for the original. When we print the results, both lists show that the 1 is now a 99. A shallow copy gives you a new outer layer, but the inner layers remain securely tied together. Changing the nested items in one will always change the other. To avoid that shared trap, we need a way to create a true clone, a second structure where absolutely nothing is shared with the original. For that, Python provides a tool called the deepcopy. Let's start fresh. This time, we use the command copy.deepcopy a. We get our new outer container, the red backpack, sitting next to our original blue one. Instead of creating glowing portals, a deep copy digs into every single layer of the original structure. It scans the backpack, sees the lunchboxes inside, and physically prints entirely new, disconnected lunchboxes to put into the red backpack. No strings attached. Now, let's run that exact same modification. We type B00 equals 99 to change the first snack inside the new red backpack. This time, the blue backpack is totally isolated. Its lunchbox still safely holds the original number 1. Our printed results confirm we have two distinct lists. By cloning every layer of your data, a deep copy ensures you can safely change your new list without leaving a single trace on the source material. Before you duplicate your data, you just have to ask yourself how much independence your new task actually needs. This chart shows our rule of thumb. On the left, if you only need to edit the outer structure, like adding a whole new lunchbox, use copy.copy. It gives you a new outside while keeping the inside shared. On the right, if you need to change the specific items buried inside the containers, use copy.deepcopy. That gives you a structure that is completely new, from top to bottom. Understanding how memory is linked lets you control exactly what happens when you alter your data. You step away from wondering why numbers are mysteriously changing, and you start building code that behaves exactly the way you expect.